All right, howdy folks. On this page, what we're going to do is talk about a synthesis problem. And as I've mentioned before, I think synthesis problems are probably one of the most complicated kinds of questions that we ask students to solve in the typical Organic 1, Organic 2 class. And the reason for that is you need to know your reactions both forward and backward, and then you need to be able to rank them in some kind of order and put them together to kind of complete a nice sequence of events. And so that makes it quite challenging. The content for this particular synthesis question I would put mostly in the chapters on aldehydes and ketones, but we'll borrow a little bit of knowledge from carboxylic acids and esters as well. So you'll notice that the product that we need to ultimately form has an ester in it. And so that's something that we'll need to build towards. All right, so what I'll do is encourage you to pause this video for a minute and actually try to work through the synthesis problem. And remember, for these synthesis problems, you can use most common kinds of reagents in organic chemistry. So the things that you typically see above or below an arrow in your class. So please take a minute, see if you can work through this all on your own, and then you can come back and we'll talk through some of the details. All right, hopefully you're coming back in with a good idea of how to solve the synthesis problem. A couple of things I usually encourage folks to do is to look through and just try to identify and count up where your carbons are. So in the in the product here, we've got 3, 4, 5, 6, 7. And by the way, you'll notice I did not count that 8th carbon. And the reason for that is that one's almost assuredly going to come in at methanol. So we're not worried about how to make methanol. What we're worried about is how to make the chain that we're supposed to put together. And so here it looks like I have, again, 1, 2, 3, 4, 5, 6, 7 carbons. And that's a little bit of a problem because I've got 3 in this starting material and I've got 3 in this starting material. And so somehow we're going to have to add 1 carbon. The good news is there's 2 common 1 carbon units that we can consider to bring into our retrosynthesis. So one of them would be carbon dioxide, and then the other one would be a cyanide anion. And so both of those are sources of 1 carbon to make a chain a little bit longer. Now, one pitfall that I think a lot of students fall into when looking at this problem is they look at this carbonyl and they look at this carbonyl, and then they think that this carbon needs to be this carbon. And it turns out that that is a very easy thing to think because those carbonyls are pretty similar and we know how to oxidize aldehydes to acids. And of course we can make esters from acids, so that seems quite logical. The only hiccup is I'm not so sure how you would make a bond at this beta carbon. And so that's a little bit further away. We know how to react at the alpha carbon with enolate chemistry, and so that's a very powerful tool to construct bonds alpha. But if we look in the product here, there's nothing alpha to that carbonyl. Not only that, there's 2 different CH2 units, and so somehow we would have to just pluck an H off of there and then just add it into another carbon-carbon group. And that's going to be quite difficult to do. And so what I would encourage you to do is, instead of considering this carbonyl to be where the ester shows up in the product, I would encourage you instead to look at this chain, because here we have a nice CH2 unit and a CH3, and so that matches this. And then there is a carbon bound to a double bond. And aha, we do know how to convert aldehydes and ketones into double bonds. And so that might include the Wittig reaction. So when doing a retrosynthetic analysis here, I might think about the Wittig reaction to go ahead and correct to put that bond in place. So I think that that is ultimately going to be a little bit more helpful. And then if we go back and start thinking about where we can put this dibromo propane group, then we would have 1 carbon here, 2, 3 carbons here. And that kind of helps out because then this one could be from either cyanide or from CO2, and we would have a functional group on both ends of that channel. And so when thinking about this retrosynthetically, again, I would encourage you not to look for the most obvious thing, because certainly looking for the carbonyl aldehyde to be part of the carbonyl on the ester seems like it makes sense, but it doesn't actually track on to a whole lot of the reactions that we know. So when filling this out, what I would encourage you to do is take the bottom approach here, and we're going to react this with PPH3. And we want to make sure that we have only one equivalent of that PPH3 so that we can make the Wittig salt. And the reason I was doing this first is because that Wittig salt should crash out of a lot of the reactions that it makes. And so there's not a whole lot of a risk that the PPH3 will add to both ends of that system. Because we have two identical functional groups on that dibromopropane, there's no good way to react one of them and not the other one because they're equivalent. And so we're going to have to rely on something else to get a high yield. Ultimately, though, the overall yield of the sequence isn't something we need to be considering at this stage. And so let's just roll with it and make the Wittig reagent. Now we can deprotonate the Wittig reagent with all sorts of strong bases. In this case, I'm going to use phenyllithium, and that's going to make our ylide. And so remember, the ylide is the double bound version of this. And then what we can do with that ylide is add in our propanal. And then we're going to crash out PPPH3 oxide. Get that? And then we will have kind of our double bond. And I'm going to make that double bond a little bit cleaner there. And so now we've had the ylide at this site attack the aldehyde at that site and put them together to make the double bond here. And so then we should have a CH2, a CH2, and a bromine. We have a CH2, a CH2, and a bromine. And so that all checks. So that's pretty good. Now, there's a couple of different ways to convert that bromine to a carboxylic acid. The one that I'm a biggest fan of is actually to use sodium cyanide. And that'll generate then the nitrile. And then we can hydrolyze that nitrile with acid and water. And if you don't like H3O plus as a reagent, remember, typically this is just water plus H2SO4 will generate some H3O plus and then some HSO4 minus as the counter ion to that hydronium ion. And so that should get us the free carboxylic acid. And then what we should be able to do from there is treat this up with some more H2SO4, and we can do that in methanol. And because then that mimics the Fischer esterification conditions, we can use a lot of methanol to push that equilibrium process forward to the methyl ester. And boom, there we go. So that'll do it. There is a second pathway we can consider, though. If I go back here, we could take this same bromide and use magnesium 0, and that would make the Grignard reagent. And then we can treat that Grignard reagent first with carbon dioxide, and then with some HCl, and that'll generate the same carboxylic acid. Now, the reason that I'm not as big of a fan of the magnesium Grignard approach is because those Grignard reagents tend to be quite water sensitive in the lab, and so there's a little bit of experimental difficulty associated with actually generating that Grignard reagent in high yield and then treating it with CO2, which has to be dry to generate the carboxylic acid. In principle, though, both would work. So if it were an exam in my class, I would grade both of these options as being fully correct. And that's really one of the fun things about synthesis is often there is more than one pathway to get where you want to go. All right, so that summarizes this video. If you're enjoying these videos, again, please do subscribe to our YouTube channel. That's very important to give encouragement for us to keep making these videos. And then secondly, if you want to follow us on Facebook or Twitter or a different social media platform, as well as our Patreon page, please do that. The Patreon page will let you download these PDF files, perhaps even before you watch the video so that you can fill them all out on your own. All right, thank you for your time. Please share with your friends.